Hi everyone. In the previous video on exact differential equations, I gave an introduction as to what exact differential equations are, and in this video, we'll be taking some examples on exact differential equation. So to start with, let's take the first question. The first question we are going to be taking a look at is this. So we're required to solve the differential equation cos x plus y dx is plus 3y squared plus 2y plus cos x plus y dy to be equal to 0. So using the method of solution that we've talked about in the previous video, we are going to try to solve this exact differential equation. So the first thing is to test for exactness of the differential equation. So in doing this, we have cos x plus y dx plus 3y squared plus 2y plus cos x plus y dy to be equal to 0. If we compare this with the general form of an exact differential equation, which is m dx plus n dy is equal to 0, we have that our m and n are given by these arrows. So our m now becomes cos x plus y, and our n is 3y squared plus 2y plus cos x plus y. Since we've identified what m and n is, we can now test for exactness. Now, recall that the condition for exactness is that the m dy must be equal to the n dx. So we can't compare this if we haven't evaluated the partial derivatives of m with respect to y and the partial derivatives of n with respect to x. So the m dy, if our m is equal to cos x plus y, so we have the m dy to be equal to, remember that when we're finding a partial derivative of m with respect to y, we keep m as a constant. Remember that when we're finding the partial derivative of m with respect to y, we keep x as a constant. So by doing that, we are going to get the partial derivative of m with respect to y to be minus sine x plus y. And to evaluate the partial derivative of n with respect to x, we have to keep y constant. But before that, let me write what n is. N is equal to 3y squared plus 2y plus cos x plus y. Now, if we want to differentiate this with respect to x, remember that we are keeping y constant. So the first two expressions here will be 0 because they are all functions in y purely, and we won't be able to differentiate that without getting 0 since y is a constant. So we ignore that, and we have just the differential of cos x plus y with respect to x. So on doing this, we are going to get the result to be minus sine x plus y. So from this, we can see that our dm dy is equal to the n dx, and this is equal to minus sine x plus y. So the conclusion we can draw from this is that the given equation is an exact differential equation. So now recall that we've completed step one. Now the second step, which is step two, is to integrate m with respect to x, keeping y constant. So to do that, we want to find the integral of m with respect to x while keeping y constant. So we are going to be having our results to be the integral of cos x plus y with respect to x. So by integrating this, if y is a constant, we are going to have our result as sine x plus y. So we've completed step two. We now have to evaluate step three, which is to integrate with respect to y only those terms of n which do not contain y. So here's what we do in step three. So we know that n is equal to 3y squared plus 2y plus cos x plus y. So the terms of n which do not contain x at all is only they are 3y squared plus 2y. So these are the terms in n which do not contain y. So we now integrate this with respect to y. We are finding the integral of 3y squared plus 2y with respect to y. So by doing this, we have 3y cubed divided by 3 plus 2y squared divided by 2, which is equal to y cubed plus y squared. So we've completed step 3. Our next step is to add the results from the steps 1 and 2 and equate it to a constant. So recall that the results from step 1 now, the results from step 2 and 3. Results from step 2 is equal to sine x plus y. And the results of step 3 is equal to y cubed plus y squared. Hence, the solution to the differential equation can now be written as sine x plus y cubed plus y squared to be equal to a constant c. So this gives the solution of the differential equation. So this is the solution of the given exact differential equation. Now remember I said the fifth step is optional. If you are sure about your solution, you don't have to do it. But if you are not sure of your solution, you can go ahead to check your result. So let's check. Now the solution to our differential equation is z is equal to sine x plus y raised to the power of 3 plus y squared, which is equal to a constant. Now recall that we said an exact differential equation is a differential equation that is obtained by directly differentiating its primitive solution without any further process. So let's try to differentiate the primitive solution here. Now let's recall that the total differential dz of z will be equal to the partial derivative of z with respect to x, keeping y constant, multiplied by dx plus the partial derivative of z with respect to y, keeping x constant. And this is going to be equal to 0 because when you differentiate the constant, you're going to be having 0. So let's evaluate. The partial derivative of z with respect to x is given as cos x plus y. When you differentiate y cubed and y squared, you're going to be having that at 0. Since they are constants here, we are keeping y constant. And the partial derivative of z with respect to y is given as cos x plus y plus 3y squared plus 2y from the expression z is equal to sine x plus y raised to the power of 3 plus y squared. So in this case, we can see now that we can substitute this into the expression for the z. Let's call it equation star. So from equation star, I could call it asterisk. We have our dz to be equal to dz dx multiplied by dx plus the partial derivative of z with respect to y multiplied by dy, which is equal to 0. So I'm substituting this. We now have cos dz is equal to cos x plus y dx plus 3y squared plus 2y plus cos x plus y dy, and this is equal to 0. Looking at this expression, we can see that it's the same expression, the same differential equation that we were given to solve. So this shows that by directly differentiating the primitive solution, which is what we got here as sine x plus y raised to the power of 3 plus y squared equal to c, which is a constant, without any further process, we can arrive back at the exact differential equation we were given in the beginning of the question. And so this has confirmed that we have the right solution to the differential equation. These exact differential equations could also be solved in a slightly different way. So using this same example, we are going to try to solve the exact differential equation in another way. So now, recall that we've checked for the exactness of the differential equation. So step 1 still holds. Step 1 has been done. So rather than separating it step 2 and step 3 and trying to integrate with respect to x first before integrating with respect to y, these steps were gotten from a particular principle, and that's what I'm about to show using this question. Now let's recall that dz dx is equal to m. This was what we did in the previous video. We can look it up just in case we don't remember this. So to get z, we can integrate both sides with respect to x. So if we integrate both sides with respect to x, we are going to be having integral of dz will be equal to integral of m dx plus a constant. And since in this case m has been gotten by the partial derivative of z with respect to x, it's safe to say whatever results we have could be assumed to be a function in y only. Because on differentiating it back, because we are going to be getting our z to be equal to integral of m dx with respect to x plus a function k in y. This is trying to tell us that when we differentiate this, our result is still going to be m because y is assumed to be a constant. So that's where this came from. So if we use that, we now have our z to be equal to the integral of cos x plus y with respect to x plus k, which is a function in y only. So this becomes sine x plus y plus k, which is a function of y. So this should be our solution of the differential equation. But we are not done. We still need to find what k is before we can conclude the solution. So to find k, we now recall that our n is equal to the partial derivative of z with respect to y. And since our z is equal to sine x plus y plus k, which is a function in y, we can find the partial derivative of z with respect to y in this case and equate it to n, which we know normally. So dz dy now becomes cos x plus y plus dk dy. And we said this is equal to n. Now we have to recall that our n is equal to 3y squared plus 2y plus cos x plus y. So now when integrating both to each other, we have cos x plus y plus dk dy is equal to 3y squared plus 2y plus cos x plus y. So by cancelling out the result on both sides, we now have our dk dy to be equal to 3y squared plus 2y. That is, cos x plus y has been cancelled out on both sides. So since we only have a function of y on the right hand side, we can rewrite this as dk dy to be equal to 3y squared plus 2y. So on cross multiplication, we have dk to be equal to 3y squared plus 2y dy. Can then integrate both sides, dk to be equal to the integral of 3y squared plus 2y with respect to y. So this becomes y cubed plus y squared plus c. Let's call this c asterisk. C asterisk is also a constant, by the way. And if we look at this, we can see that this is similar to the result we obtained when we said we should differentiate the terms of n which do not contain x at all with respect to y. That is the same thing. The first part was similar to step 2 where we said we should differentiate m, we should integrate m with respect to x. So that's just step 2 and step 3 that has been combined together. So this is just a method to show how those steps were arrived at. So we said that our z is equal to sine x plus y plus ky. We can see that from the result we've obtained, this is what our k, which is a function in y, is. So our z becomes sine x plus y plus y cubed plus y squared plus c asterisk, which is equal to 0. So we can write this as z is equal to sine x plus y cube plus y squared is equal to minus c asterisk. So let's bring our result back here. So we have our z is equal to sine x plus y raised to the power of 3 plus y squared, which is equal to minus c asterisk. So if we allow minus c asterisk to be equal to c, we can write this as z is equal to sine x plus y raised to the power 3 plus y squared to be equal to c. So this gives the solution of the exact differential equation just as we obtained in the other method. So thank you very much for watching this video and see you all in the next video.